titled Properties of Linear Systems. So our introduction then acquainted us with the state space formulation and how we extract certain information from that, including eigenvectors and eigenvalues, and the dynamic response, and then the connection between the state space representation and the transfer function representation. This section goes a little bit further and examines the properties of the state space formulation, and there are three in particular which are very important, plus a couple of others that you might not have imagined. The most obvious of the properties is that of stability, and you probably have a very clear image in your mind what is meant by stability, and it's obvious, I think, for stable systems, for a continuous time system, transfer function systems, what stable means. Right, you know it when you see it. It's either something that remains bounded or doesn't remain bounded, and that's nice. But for the state space description, where we have a set of internal variables, there are a couple of other classifications of stability which are important. And when you take the theory further, if you go on to study nonlinear systems, you'll find that stability is a very nebulous concept indeed. There are systems that kind of look as if they're stable and look as if they're unstable at the same time. So I need to explain stability from the context of the state space description, and particularly from the state vector perspective. And then there are two properties which are unique to the state space description. Those are called controllability and observability. They don't apply to the transfer function description, but they do apply to the state space description. And they're very important because when we later go on to design control systems using the state space paradigm, if the system is not controllable, our effort will be futile. And then still later, when we go on to design an estimator or an observer, that's the same thing. If the system we begin with is not observable, similarly, our efforts will be futile. We can't estimate the states from an unobservable system. So controllability and observability are important properties that we'll need later. Now, it turns out that stability, as well as controllability and observability, all these three have a very clear visualization if we can carry out a specific kind of transformation on the system called a modal decomposition. I'm going to explain to you what modal decomposition actually means, but if you can carry one out, all these properties become very clear to you, and there are other benefits towards doing it as well. So we'll start with modal decomposition, and then I'm going to show you the properties explained in that term and in terms of other things as well. And then we'll look at canonical realizations again. I've shown you one, phase variable canonical form. It turns out that there are two others called the controllable canonical form and the observable canonical form, which is why this section comes right after that one about controllability and observability. And then the very last thing I'm going to do, it's a fairly short section, the last thing before lunch, is to introduce the next tutorial that is going to be more or less every tutorial after this will be based on it. It's a double mass system. It consists of a mechanical system having two masses which are coupled together by a very lightly damped coupling, such that when you push one mass, the other mass moves, but there's some kind of energy exchange between the two masses, and the result is oscillatory. It's a nice, easy to visualize system, and it has a lot of the dynamics that make these tutorials fun to do and interesting at the same time. So I'm going to introduce that system at the end of this section. Now, I want to begin by explaining the concept of similar matrices. When matrices are used for transformations, you've seen that in n dimensions, the matrix has dimensions n by n. The matrix is square. And so, therefore, if we have a transformation from one vector to another in three-dimensional space, the transformation matrix which performs that is three-dimensional. Here, for example, we have a vector v, which is operated on by a matrix T1 to transform the vector to a different vector called v tilde. So v tilde is pointing in a different direction than v because it's been operated on by the matrix T1. Now T1, as well as v and v tilde, will be expressed in terms of a coordinate system that might be orthogonal. For example, x1, y1, and z1, those might be three orthogonal coordinates which represent the vectors and the transformation between them. Now let's imagine that we change nothing but the coordinate system in which all this information is presented. Instead of x1, y1, z1, we use x2, y2, z2. Well, now the same two matrices, same two vectors would have a slightly different representation because their elements would be different, because although they're pointing in the same direction notionally, they're represented in a different coordinate frame. And the transformation matrix, which moves from V to V tilde, that would be different too, because its coordinate frame had changed. It's doing exactly the same thing, but it's doing it in a different coordinate frame. Matrices T1 and T2 are called similar matrices. They perform exactly the same transformation, but they perform it in a different coordinate frame. They're related by a transformation called a similarity transformation. In particular, T2 is equal to m to the minus 1 T1 times m, where m is a similarity transformation. It transforms a matrix from one coordinate frame into another coordinate frame. It has a very specific form, doesn't it? You see the matrix M, it must be square, it must have the same dimensions as T, because T2 has the same dimensions as T1, but m to the minus 1 times that times m, when you see that, think similarity transformation. It's going to come in just a second. Now, this is an important point, so let me spend a couple of minutes to describing it. It is possible to find a similarity transformation matrix M, which takes T1 and makes T2 diagonal, right? And if you can do that, then there's a lot of benefits that come out of that particular representation, that particular coordinate frame. But in order for that to happen, T1 must have a full set of eigenvectors. Otherwise, you can't diagonalize T2. If T1 has not got a full set of eigenvectors, you can't have a fully diagonal T2, but you can get close to it. The form of the matrix which appears is called a Jordan form representation, which I'm going to explain shortly. But let's for now imagine that we've got a full set of eigenvectors in T1, and that some similarity transformation can be found such that the diagonal matrix T2, which results, well, that matrix is diagonal, but it has a further property, which is that you can arrange the elements of the diagonal matrix such that they are the eigenvalues of the system. And the similarity transformation which does that for you has columns which are themselves the eigenvectors of T1. So there's some important information there that I want to repeat. If T1 has a full set of eigenvectors, the eigenvectors are by definition linearly independent. Those eigenvectors can be used as columns to form the similarity transformation matrix M. It's okay for dimensions because you know you've got n eigenvalues in T1. T1 is n by n, and you've got a full set of eigenvalues. You've got n eigenvectors, and each eigenvector has n elements in it. So by making those columns, the columns of M, M must also be n by n in dimension. And by using that matrix, which results in a similarity transformation, T2 will be diagonal, but not only diagonal, the eigenvalues of T1 will be the elements of the diagonal on T2. Now, before I use that information, I'm going to introduce you to how you make a state transformation from a state, using a state equation. Now, let's say that I've written a state equation for a system based on a particular choice of state elements. And I told you previously that there was nothing unique about those state elements. You can pick anything you like. So let's pretend that you make one choice and it's not working out well for you. You want to change them to a different set of elements. There's no reason why you can't do that. And the change can be accomplished by what's called a state transformation. So let's say you're using X and you want to translate use V instead. V is a different, it's a state vector, but I'm just calling it V for now. And it's related to X through this matrix M, which is some arbitrary matrix now for M. So what we'll do is plug this directly into the state equation, X dot equals AX plus B. So the left-hand side is not X dot anymore, but it's M times V dot. V dot is the new state vector, equals AMV. MV is just plugged in where X was before, plus B times U. B doesn't change. Right? And now what we'll do is we'll pre-multiply both sides by the inverse of M. Now, this is a nice thing if you can make M composed of the eigenvectors, because M will be definitely invertible. So you can definitely find an inverse from M. It's square, so the dimensions are exactly what we need. And pre-multiplying both sides by the inverse of M, you get V dot equals M to the minus 1A times M times V. Look, similarity transformation on the state vector, think, plus m to the minus 1 times b times u. We've performed a similarity matrix transformation on the state vector, and guess what that m to the minus 1 am matrix is going to be? It's going to be diagonal, and it's going to have the eigenvalues along the leading diagonal. Let's call it A1, and let's call m to the minus 1b D1. Now, that's the state vector into the transformed state. We now need to concentrate on the output equation, and we do the same thing, but it's much simpler because we don't have to invert m. All we need is to replace x by m times v, and we'll call that C1. So C times m is going to be C1 plus d times ud is unaffected by all of this. So now we have the state equation and the output equation represented in terms of this new state, v, whatever v happens to be. Now, the unique choice of, so there's an infinite choice of it. You can pick any states you like, so we're not tied to a particular state. You can change freely between one and the other. But for this unique choice, the elements of V have a particular name. They're called the modes of the system. Physical systems operate in a characteristic set of patterns, as it's said here. Those patterns are called modes, and it's a unique choice of the elements of the state vector which are called modes. And the reason that they're important is that you'll see in a moment, each of the modes is completely uncoupled from all the other modes. This transformation, the unique transformation where you've used this M matrix of eigenvector columns to transform into using it in a state vector transformation, that's called modal decomposition. And there are many reasons why you might want to do it. The first is the fact that these modes are uncoupled from one another gives us a very clear visualization of the pathways between the input and the output. Not only that, but the pathways from the input and the state to the output are much clearer than they would be if you just taken a random state vector representation. The dynamics are much easier to solve because they're scalar, not vector. It gives a very simple view of motion over time, and it makes it clear where the dynamics of the system are. Because by exposing where the eigenvalues are, you know which are the dominant modes and which are less important. Remember, the modes to the left in the complex plane, the eigenvalues to the left in the complex plane are decaying more quickly than those to the right, those closer to the imaginary axis, if it's a continuous time system, and there are parallels to that if it's a discrete time system. You also get a much clearer insight into the two properties I explained earlier of controllability and observability, and the reason for that is that the pathways are exposed in a modal decomposition. And the process is similar for a continuous time or a discrete time system. It's just that the meaning of the eigenvalues is different. So let's do it. We're going to compose this modal similarity transformation matrix, which I'm now going to call W because it's a very specific transformation matrix. M might be a general one, but I want to call this W. And the columns of W are composed of the n independent eigenvalues, n independent eigenvectors of the system matrix A, right? So you've got n columns, each column having n elements. This is an n by n matrix. And I'm going to change notation for the vector as well because it's such a specific and a unique choice of elements called modes. I'm going to give it the symbol Q, and the elements will be Q1 to Q sub n. These are the modes of the system. So yeah, this is what it is. Now, there's another notational change I want to make you aware of. So this is the new state equation, and this is the new output equation. And because of this unique choice of columns for the transformation matrix W, we, as I said, end up with a diagonalized new system matrix, lambda. This is an uppercase lambda, and lambda will contain along its leading diagonal the eigenvectors of A. So writing these equations, I guess, this is how they look. The modal matrix, as it's called, contains in its columns the eigenvectors of A, and the spectral matrix, as it's called, lambda, is a diagonal matrix where the eigenvalues lie along the leading diagonal and all the other elements are zero. So modal matrix and spectral matrix are the names that are applied to these two. Now the modal input matrix is W to the minus 1 times B. So we plug W into that state transformation formula that I showed you. Lambda I've explained. Now the input matrix, W to the minus 1B. Now when you So when you use this decomposition, it's helpful to separate out the individual rows of this input matrix. So I'm calling these rows beta 1, beta 2, all the way to beta sub n. And these are the rows of w to the minus 1b, which is why I'm writing it like this. So think of these as vectors, but actually they're row vectors, and there are n of them in the n rows of the input matrix now. Okay, so beta 1 to beta sub n are the rows of the input matrix w to the minus 1b. And therefore, this is what your state equation looks like in full form. The derivative of the modal vector on the left equals the spectral matrix times the modal vector plus, and then these are the rows of the new modal input matrix, but I'm thinking of them as vectors times the input vector. So if you like, it's the beta i's which capture the coupling of all the inputs onto a specific mode, right? And then the lambda I captures the dynamics from qi to qi dot. So you see what I mean about complete decoupling now, if you can write the state equation in this form. That's the modal input matrix, and that's how it looks about. It looks in for each individual mode, right? That's the equation that you've got. So notice now that this lambda I appearing here, this is totally scalar. And the key point is that the dynamics are uncoupled. That's the input matrix. Modal response, previously the state could have, every state derivative could have involved all the other states, because you might have had a row of the state matrix which had every element non-zero in it. But now what you've got is only a single first-order differential equation involving the same mode, right? The other modes don't take any effect in that. And this is the solution to the mode. Yeah. So it's the eigenvalue now that fixes the transient response. That gives you the growth or the decay of the modal evolution. And then the particular integral involves beta I. So that gives us the shape of the response. It's the eigenvectors that determine that through their relationship with B. The output matrix is the product of C and W, and it's helpful in what follows to think of the columns of the CW matrix as separate vectors. And there are n of them, because this will multiply up into a vector. So gamma 1 to gamma n, separate vectors, each vector coupling a single mode onto all the outputs. Okay, so this is what it would look like. I mean, they're vectors, but think of them at least for now as scalars. Each gamma I, as I say, coupling a particular mode onto all the outputs together, so that the output vector is the sum of all these products. So gamma 1 times Q1 plus gamma 2 times Q2, and so on. Now, this diagram, I think, will tie it all together, because this is graphically what we've done. We've changed the sort of nebulous representation in state space into a completely separate set of states, each of which is completely decoupled from all the others. And it's scalar now, because Qi depends only on Qi dot, and vice versa. And the coupling between the I state and all the inputs is determined by the corresponding row of the modal input matrix. And the coupling between the ith state and all the outputs is determined by the ith column of the modal output matrix. So can you see now you've got a very clear visualization of how all the inputs affect one mode and how the mode affects all the outputs. It's very obvious in this representation how that happens. Now, everything works fine, providing that you've got a full set of eigenvectors. And if you haven't, the only way that you can have had that is if you've got repeated eigenvalues. So before I go on and tell you how you use this information to describe the properties of a system, I want to just touch briefly on what goes wrong if you've got a degenerate system matrix. It can only happen with repeated eigenvalues, and even then, it may not happen. You may be lucky and say, well, you've got repeated eigenvalues, but you've still got a full set of eigenvectors. Or you may be unlucky and lose one or more of the eigenvectors. So the systems are degenerate, and when you lose eigenvectors, you have to, if you want to carry out a modal decomposition, you have to replace them by substituting the missing ones with eigenvectors that are called generalized eigenvectors. These will still be orthogonal to the true eigenvectors, but they won't themselves satisfy the eigenvector equation that I showed you before, which is A minus lambda I times Wi, and we looked for a non-trivial solution to that. So they're generalized eigenvectors. You can find them through MATLAB. There is a lengthy process to find them, which I don't intend to cover in today's seminar. But once you've found those, you can use them in a modal transformation. But the spectral matrix, the one with the diagonal eigenvalues in it, won't be truly diagonal anymore. It'll have some elements in the superdiagonal which are 1, which means that the modes won't be perfectly decoupled from all the others. There'll be a little bit of coupling going on. And the form of a matrix which has that, diagonal but with some superdiagonal equal to 1, they're called Jordan matrices. And the matrix, system matrix, which results, called the spectral matrix, will have Jordan blocks in it. Right? Now, there are different possible permutations when you start to lose matrices, but fundamentally, the number of eigenvectors that you get for a specific eigenvalue depends on how many solutions you get to the formula A minus I times lambda I times Wi equals 0. That was how you found the eigenvectors, remember? And you did that for every choice of lambda I. Now, if some lambda i's are the same, you might lose solutions. You might not have fully independent solutions to that. And the number that you get depends on the null space dimension of this matrix, A minus I times lambda I. The null space dimension tells you how many eigenvectors you're going to get out for that specific lambda I. So in this case, there's an integer that I'm calling hi, which tells you the number of available eigenvectors for a specific eigenvalue. And the number will be between 1, you'll always get 1, and mi, which is the multiplicity of that particular eigenvalue. If you're lucky, you get a full set, in which case you've got what's called full degeneracy and nothing need worry us. But if you've got less than that, well, if you've only got 1, you need these generalized eigenvalues, and you end up with a full Jordan form representation. If you've got between 1 and the multiplicity, well, you end up with Jordan blocks appearing, and the spectral matrix has certain blocks in it which have 1s on the superdiagonals, but they're not all 1s. Some of them are 0s. Let me show you a quick example of this. This is a Jordan block, right, which might be associated with a specific eigenvalue that has some multiplicity, and the multiplicity is the number of elements on the diagonal. And you see that all the elements are 0 except these few. This is called a Jordan block or Jordan matrix, if this is the only matrix there is. And as an example of it, here is a fifth-order system which has 3 eigenvalues. So there are 2 missing eigenvalues. I've got 2 at minus 2, 2 at plus 3, so it's an unstable system, and 1 at minus 1. And so in this case, what appears is for the 2 eigenvalues at minus 2, there's a Jordan block there. You see that? It's on the diagonal, such that the eigenvalues appear on the diagonal, but the generalized eigenvector that we need puts a 1 there. And then same thing for the 3. There's a Jordan block appearing here with 3's on the diagonal and 1 in the superdiagonal, and then the single real eigenvalue gives us an eigenvector associated with it, so you get a nice minus 1 in the bottom right-hand corner like that. I'm going to do a quick tutorial now, just to show you how you use the modal decomposition. And for once, it's not based on the buck converter anymore. Bear with me while I clear everything else out. In this case, what we're doing in tutorial 6.1 is to decompose. I have no idea what I did there. I apologize for it. Pressed something I shouldn't have done. Decompose this into its constituent modes. So clearly this is a third-order system. I don't know how well behaved it's going to be, but it obviously has 2 inputs because the input matrix has 2 columns in it. So we've got 3 states, and we've got 2 inputs, and we have a single output because of the form of the output matrix C. It has 1 row, so there must be 1 output, and it has 3 columns because we know there are 3 states. And the input matrix is 0. So transmission matrix, I'm sorry, is 0. It's got two elements in it because there are two inputs, and it has one row because there's one output. So let's decompose this into its constituent modes, and we'll see what happens. So to begin with, then, all we do is construct the system using the same methods that I've shown you before in MATLAB. And before we do the modal decomposition, I'm going to plot its response, and we'll see how this response changes after modal decomposition. First of all, I'm going to construct a step response of this and plot the three modes. Now, the problem is that there are two inputs. So what's a step response? The reason is that there's two step inputs to this, because what MATLAB will do when you conduct a step response on a system with two inputs is it will give you two sets of results. One, which is a step applied to the first input while the second's held 0, and the other set of results when the first is held 0 and the second has the step input applied to it. So there's going to be two sets of state graphs here. Right, that'll be reflected in the dimensions of the state vectors that come out of this, the state vector results. So here we go. Here are the two results. The upper graph is the evolution of the three internal states when we have a step applied to U1 and U2 is held 0. And then the reverse for the bottom graph down here. These are the states evolution over time as U1 is held constant and then U2 is, has a step applied to it. Now, what we'll do is perform a modal decomposition, and this is how we do it. This CLC just clears whatever's in the workspace. That makes things a little bit tidy for us. And then I'm going to use the Eig instruction again. Remember, that's the one that we extracted the eigenvalues from. But when you use that instruction with these two parameters on the left, W and L, it will return for us the modal matrix W and the spectral matrix lambda. Well, there isn't a character on the keyboard for lambda, so I'm using uppercase L. Those are the two matrices, both n by n, 3 by 3 in this case, which are returned. You give it the spectral matrix, the system matrix A, and no balance just means don't balance out the eigenvectors. I mean, I'd just like to do it that way, but it doesn't matter. Now you've got hold of W, you can use that in a similarity transformation to extract the modal input and modal output matrices. Remember, modal input matrix was W to the minus 1 times B, so we'll invert W and multiply it by B, and I'm interested in the, well, I'm going to transpose it because of the interest in the treating the rows as vectors. You'll see why in a second. And then the modal output matrix is C times W. And then what we'll do is just represent them as the modal matrix. So let's do this, and what you'll see is the A, B, C, and D disappear, and what we end up with is L, M, I, M, 0, and D. I don't know why we didn't end up with it. Oh, okay, all right. So all it's done is just given me A, B, C, and D again. But the point is, this is the spectral matrix. This is lambda, consisting of the eigenvalues in a diagonal matrix. This is the modal input matrix. It's transposed. I wonder why it's transposed. That's actually the right form. I'd have to think about why it was transposed, but that is the right form of input matrix because it has two columns, there are two inputs, and then there are three rows because there are three states in this. And then there's the output matrix, modal output matrix, and the transmission matrix is still 0. And then what we'll do is exactly the same thing as we did before we carried out the modal decomposition. We'll conduct a step response and plot the states. And now here's the thing. For this particular choice of states, because we've got a fully diagonalized spectral matrix, we must have fully decoupled internal states now. Each state is only dependent on its own state. So we've got Qi of t equals lambda I times Qi. So they're fully decoupled. It's a first-order differential equation. There's nothing else in there. And you know from yesterday that the solution to a first-order differential equation is exponential. So when we compute the states and we work them out for a step input, we should find 1 minus a decaying exponential for every single state. And what we get is indeed that. So these are the states and how they evolve now for a step input because they're all decoupled from one another. Now you might look at that and think, well, okay, it's telling us that, so what? Maybe the system's changed too. But the point is, because it's only a state transformation, the actual dynamics of the system don't change. In other words, as a whole, the system will behave exactly the same whether I've represented the states using some arbitrary selection or this particular selection. And I'm going to show you that. Now, what I'm going to do is, first of all, plot the original system. This is the plot of Y1, which was the output of the original system, and it looks like that. All right, there's nothing very interesting about that. That's how the system will behave. And now what I'm going to do down below here is the same thing. I'm going to plot on top of this graph Y2 being the output of the modal decomposition, and all that will change, I hope, is the color of that plot. It should go from blue to green, because it's the same system. It's only the internal dynamics which are represented differently by a different choice of states. That's what a modal decomposition is doing for us. Okay? The main reason for using a modal decomposition is that the pathways from the input to the output are much clearer. And that property means that the properties of controllability, observability, stability, and so on are much easier to visualize, which we're going to see now. It's a good point because it leads me into what's coming next. It's possible, yeah. Yeah. Well, it will help in the sense that it might focus your attention on the dominant modes. So it might help in that sense. Or if you wanted to simplify a system by reducing the order of it, it might help you in making that choice too. So there are reasons why it would help with control design. Yes, exactly. Well, sort of. Yeah, you're right. But I want to get away from the idea of lead and lag compensators and also from root locus. Because with the system I described yesterday where we used output feedback, we were obliged to put the closed loop poles on specific lines in the complex plane called loci. And the only thing that we could change was the gain to move the poles along those loci. One of the big advantages with state feedback control is that you can choose anywhere you like in the complex plane to put the poles. You have a far greater degree of flexibility for where the closed-loop poles go. The fact that you're using the state vector in the feedback rather than just the output is that benefit. So, yeah, I think this helps also with that process of making the selection of closed-loop poles. Now, I'm going to use this a little bit more in a moment, but I want to go on and talk about stability in a moment. And there are two types of stability that I want to tell you about before we go on and see how they're used. The first is what we might immediately think of as a stable system. This system possesses the property called asymptotic stability, which means that its state, the initial condition response of its state, as time becomes infinite, will converge on the equilibrium point. So this would be equivalent to a stable node or a stable focus in the phase portraits that I showed you earlier, because the state might follow some sort of a path. This one is a stable focus, where eventually over time it settles in its steady state on the equilibrium point. It's called asymptotic stability, and there is a wordy definition for what it means in terms of how far you displace the initial condition and the fact that it converges on the equilibrium point. So systems which have, if they're continuous time, eigenvalues less than 0, or if they're discrete time, eigenvalues of modulus less than 1, have the property of asymptotic stability. Now, while we're on this slide, can I just make something that looks obvious very clear to you, so it's doubly obvious because it matters later. In the steady state for an asymptotic stable system, if it's continuous time, you know that the steady state is defined by x dot of t equals 0. It means that the state isn't changing anymore. It's reached its equilibrium point, and that is the steady state. But notice, if it's a discrete time system, there's a difference, because what it means in steady state is that the next state is no different from the current state. And so the state xk plus 1 is the same as xk. And so when you look at the steady state for a discrete time system, the important thing is that the right-hand side is not 0 anymore. This will come back when we look at designing for steady state in feedback control systems this afternoon, but I want to make you aware that that's an important difference, and it's practically the only one which accounts for the difference between continuous time and discrete time systems later on. So there's a difference in the steady state definition. But anyway, I think you can, perhaps later enough, imagine what asymptotic stability is. Now there's another kind of stability which was in the phase portrait diagrams where the equilibrium point was called a center. And in general, that is known as Lyapunov stability. And what Lyapunov stability says is that if you displace the initial state from its equilibrium point and let it go, providing you don't let it go too far from the state, it will either converge on the state or it might not go to infinity. It might sort of remain in the vicinity of the equilibrium point without ever actually reaching it. And an example of that is a system which has complex conjugate eigenvalues if it's continuous time, or eigenvalues on the unit circle if it's discrete time, because those oscillations are sustained. It's on the border between stable and unstable. It's called Lyapunov. Sometimes you see systems which have Lyapunov stability referred to as stable, ISL, in the sense of Lyapunov. It's not something we need to worry about too much, but the terminology comes up from time to time, particularly with relevance to nonlinear systems. But a system which does this, and in this case it's second order, so its phase portrait would fall into the category of center, it possesses Lyapunov stability. Now, both of these diagrams were drawn in terms of the state, the initial condition response of the state. What I'm going to talk about now is how the input is involved, because the effect of the input allows us to differentiate between internal and external stability. First of all, internal stability is a property of coupling between the input and the states. It's sometimes called bounded input, bounded state stability, or BIDS stability, and sometimes it's called internal stability because we're talking about an internal set of variables called the states. Providing that for a bounded input, the state remains bounded, you've got BIDS, or internal stability. And if you address the question of stability from the input to the output, then clearly you're only looking at external signals, and the property of external stability is defined when a bounded input only produces a bounded output. You have BIBO stability. Now, because the output equation is an algebraic equation only involving the states, providing that you've got bounded input, bounded state stability, you've automatically got bounded input, bounded output stability, because the dynamics are only there in the state equation, but not the reverse. It's not necessarily true that because a system is stable externally, it's also stable internally. To determine that, you need to determine how the states are coupled from the internal to the outputs, from the states to the outputs. It might be that you have internal states which are oscillating like crazy, but that oscillation isn't coupled through to the output because there are elements in the output matrix which are zero. So internal stability definitely guarantees external stability, but not the reverse. Okay, now let's go and talk about controllability and observability, and stability concept will also come into this. What I have here is a fourth order system after modal decomposition has been carried out. It's similar to the diagram that I showed before, because each of these modes is completely uncoupled from all the others, and the coupling between the inputs and each mode is determined by the rows of the W-1V matrix, and the coupling from each mode to all of the outputs by the columns of the CW matrix, these gamma elements. Now, where all the corresponding row of W-1V, so that BI transpose is non-zero and gamma I is non-zero, obviously that mode is coupled through. So you could say that because of the input is coupled to that mode, I can influence that mode by influencing the inputs. Therefore, that mode is said to be controllable. And because that corresponding column of the CW matrix is non-zero, as this mode moves, it's somehow going to influence at least one of the outputs. So therefore, the motion of that mode is observable at the output. Mode 1 is said to be controllable and observable, and you can see it on this diagram because you know that the corresponding vectors, beta 1 and gamma 1, are non-zero. Now, imagine a situation where gamma 2 is 0. That means that this mode is not coupled through to the output. We have no way of determining, simply by observing the output, whether Q2 is a stable or an unstable mode. And so therefore that mode is unobservable. But because beta 2 is non-zero, it is coupled to the input, so we could influence it. It's a controllable but unobservable mode. When the reverse is true, you can see what's going to happen with mode 3. Beta 3 is 0, but gamma 3 is non-zero, so this mode is uncontrollable, but at least it's observable. And finally, there's a mode here which is uncoupled to anything. It's an uncontrollable and unobservable mode. So these properties are very clear once you have a full modal decomposition. The significance of them is, well, first of all, as I said, you can't determine anything about the internal controllability or observability from the transfer function description. These are properties only of the state space description. And happily, most physical systems are both controllable and observable, which means when you construct a state space model from scratch of a system of some kind, the actual system itself is going to be controllable and observable, but your model usually contains some simplifications of some assumptions, which means that the model may not have those properties, and therefore you may not be able to control your model of the system or observe your model of the system. If your choice of states does have these properties, then carrying out a state transformation does not change the properties. So it doesn't matter what state selection you use, the properties of controllability and observability are unique to the system, not to the selection of states. And you tend to have problems for a variety of reasons, most often because you've forgotten that there are pole zero cancellations taking place in your transfer function description, or that the equivalent transfer function description does have cancelling poles and zeros, but you may run into it for other reasons, such as making a poor choice of states or perhaps the number of states. Those things can also lead to the loss of controllability or observability. So first of all, controllability, summarizing what was 2 slides ago, the system on the left is controllable because just looking at the dynamics, connected pathways from the input to the modes, both of the beta 1 and beta 2 column matrix vectors are non-zero. So Q1 and Q2 are both coupled to the input. So this is a controllable system. And the system on the right is uncontrollable as a general classification, but it's specifically mode 2, which is uncontrollable because mode 2 is not connected to the input. Beta 2 is a 0 vector. And that's important because this particular eigenvalue lies in the right half plane. It means that the system is unstable, and there ain't anything that we can do about that because we've got no way of influencing the unstable mode. See, this kind of thing may not be so obvious if you just have a random choice of state variables and a full state variable description, but it's obvious now that there is an unstable and uncontrollable mode present in the system, and that's going to lead to problems later. So if you have a modal decomposition, the classification between controllable and uncontrollable is very clear to you. You just look for non-zero beta I vectors. Now, that's the easy way of seeing things. There is also an algebraic test which you can apply in the general case. And the algebraic test goes like this. You first have to construct a controllability matrix, which from now on I'm going to call P. The controllability matrix looks like this. Now, this is called a partitioned matrix. I think it was in the matrix algebra notes from yesterday. The partitioned matrix contains elements which are themselves matrices. And this particular one is formed as follows. It's B, A times B, A squared B, all the way up to A to the n minus 1 times B. Now, let's think about the dimensions of this. B, is an M by R matrix. It has n rows and R columns. A is a square matrix, so it's not going to change the number of rows that are present. So AB is going to give you also an n by R matrix. A squared B, similarly, n by R. So each of these partitions is n by R. So you have n columns in the whole thing, and n times R, you have n rows, and you have n times R columns in this whole matrix. And then what you do is you look at its rank. Now remember, the rank of a matrix is the dimension of the largest non-zero determinant anywhere in it. So what's the biggest rank that you can have for this matrix? It can't get bigger than n, right? Because it has n rows in it, and it has n times R columns. So if you've got one input, it's going to be an n by n matrix. That's the biggest rank. If you've got 10 inputs, it's going to be n times 10n. But it can't get bigger than n because you need a square matrix to have a determinant. So the biggest rank you can have is n. Now, if this particular matrix has rank n, the system is controllable. That's how you do it. You can also do it for discrete time systems, and the only difference is a notational change, phi for A and gamma for B. Otherwise, you construct the controllability matrix and assess it in exactly the same way. There are some things you can say. If you've only got a rank of V, where V is less than n, then you know that you've only got V controllable nodes, and you've got n minus V uncontrollable nodes because n minus V beta I vectors are 0 in there. And some people define a controllability index as, well, it's the smallest number of partitions which must be added until you get full rank. Obviously the minimum number being, well, anyway, that's a controllability index. Now, observability is very similar, surprisingly similar, alarmingly similar. I've got a question, yes? Yeah. Sure. Yeah. You're going to say that it's not going to change. It's going to stay at 0 forever. Is that what you mean? Yeah. Yeah. How is it going to be excited? Yeah. The answer is mathematically, this thing will stay at 0 forever. In reality, it won't. There are noise and disturbances affecting systems in reality, which you just don't know. They're not going to. It's not going to stay at 0. But you've identified the fact that you can't influence it through the input, and therefore, whatever happens to it, you can't change, and it is going to grow because there will be some disturbance which excites it, and then it practically grows. But mathematically, you're right. There is nothing to excite it, so theoretically, it would stay at 0 forever. But that's not reality. Yeah, that's the answer. Is that okay? Yes. Okay, so continuing on to observability, nothing very surprising happens. We address the question of observability to the pathways between the modes and the output, and it's the columns of the CW matrix which give us that information. If they are all non-zero, then all of the modes are coupled through the output, because gamma 1, for example, determines how Q1 is coupled onto all of the outputs. And so on the left, we have an observable system. It's still an unstable system because lambda 1 is greater than 0, and it's a continuous time system. You can see that. So therefore, this mode is going to oscillate, but at least we can detect that oscillation at the output. That's the definition of observability. And on the right, I have an unstable system. It has, I think, the same modes, so that the same eigenvalues, but it's unobservable because gamma 2 is 0. The second column of the CW matrix is 0, and therefore the second mode is not connected through to any of the outputs, and we have no way of detecting what the second mode is going to do. There's an algebraic test for this as well. It involves forming a partition matrix, which I'm going to call Q. From now on, P and Q are going to be reserved for these two matrices because we're going to need them a lot. And now the partitions are formed from C transpose, A transpose, C transpose, A transpose squared, C transpose, and so on. And you look for a rank of n in this matrix. And if you have it, then the system is observable. If you don't have it, the system is unobservable. There is a parallel one for discrete time systems with A replaced by phi. Okay. Now there are two additional properties which are relevant, and the first of them is called stabilizability. Stabilizability is the same as controllability, but the question is addressed only to the unstable modes. So let me give you an example. Here is a system which has, it's an uncontrollable system because we know that the first mode is uncoupled to the input because beta 1 is 0. And therefore this mode can do whatever it likes. There's no way that we can influence this mode, but it is a stable mode. right? At least it's stable. The second mode, however, is unstable, but it has a non-zero beta 2 vector. Therefore, it is coupled through to the input, and therefore we can influence it. We could stabilize that by manipulation of the input. So this system is uncontrollable, seen as a whole, but at least it's stabilizable. You can stabilize it. There is another term which is the same as this, but it's applied to the outputs. It's called detectability. It's observability, but addressed only to the unstable modes. Here, it's the same system actually, but here you've got gamma y non-zero, so gamma 1 non-zero, so the first mode is coupled through to the outputs, but the second mode is not. Now here, the first mode is unstable, so therefore it's a detectable system based on the first mode, and the second mode is stable. And though it's not observable, because it's stable, the system is said to be detectable, meaning that if there's any internal oscillation involved, anything that's unstable inside the system, at least you can detect that. So I've defined controllability and observability in two ways, and I've defined stabilizability and detectability, which are controllability and observability, but addressed only to those two modes. Addressed only to the unstable modes. Let's do a very quick tutorial because this is quite fun, really. We're going to investigate the structural properties of this fourth-order system, and I have no idea what they are because I can't remember how this tutorial turns out. So let's look at tutorial 6.2. So first of all, we'll create the system. Nothing very surprising there, just using SS, ABCD. And first of all, we'll conduct stability analysis. Now, there's a handy script in MATLAB. You don't have to worry about things like eigenvectors and eigenvalues and working out whether left half plane or right half plane. You just type is stable. Is stable, it takes all the hard work, takes all the fun out of it, really, doesn't it? So what you do is you type is stable, is it stable, unstable? Yeah, apparently this is an unstable system. We don't know why yet, but it's an unstable system. Now, the next thing we're going to do is check controllability. First thing I'm doing here is I'm looking at the size of the A matrix. This will tell you the dimension of, now if you type 1 here, it'll tell you the number of rows, and if you type 2, it'll tell you the number of columns, because they're the dimensions, 1, 2. But I know A is a square matrix, so it doesn't really matter. This will tell me what the dimension of the system is, and of course, in this case, it's 4. And then here is the important line, because this is constructing the controllability matrix. CTRB constructs the controllability matrix from the two matrices that you need to give it, which is the system matrix A and the input matrix B. Therefore, we've created P, and now I just need to see whether the rank of P is the same as the dimension of A, which is the rank of the system, and the size of the system. And if it is, then this system is controllable, and if it's not, it's uncontrollable, and happily this is a controllable system. So there's an unstable mode in there somewhere, but at least it's controllable. So therefore you can say that this system is stabilizable, even though it's unstable. Now we'll do a similar thing for observability. I'm going to construct the observability matrix Q using OBSV, give it the A and C matrices, and again check for the rank, and hopefully the rank will be equal to 4. And unfortunately it's not. There is a rank of less than 4, and therefore the system is unobservable. And in an attempt to try and unravel some of the mystery behind this system, we'll conduct a modal decomposition and find out why. So we're going to do Eig of A. That'll give us the modal and spectral matrices, and then compute the modal input and output matrices. That's what's going on in the next script. So there we are. And now, before we go any further with this, some of the properties are now becoming clear, because all we've done is a modal decomposition. We've got, obviously, a complete set of eigenvalues and a complete set of eigenvectors, because all the eigenvalues are different, and therefore we know we've got a full set of eigenvectors. But if you look at them, left half plane, you've got a +1. So that's the reason the system's unstable. There's a positive eigenvalue in there. Lambda 3 is positive. Well, we knew that it was a controllable system, so we shouldn't be too surprised to find that all the rows of the input matrix are non-zero. But we also knew it was unobservable, meaning that some of the modes are not coupled through to the output, and lo and behold, the first two columns of the output matrix are 0. So gamma 1, gamma 2 are both 0, but gamma 3 and gamma 4 are not 0. So we've got no unstable, we've got controllable, we've got unobservable. Now, the other two properties I told you about were stabilizability and detectability. So let's deal with stabilizability first. Is this a stabilizable system? Yes. Vishal says yes. Everybody agree it's stabilizable. It is stabilizable because all of the modes are coupled to the inputs, right? So it doesn't matter that one of the modes is unstable, it's coupled through, so therefore it must be stabilizable. Is this a detectable system? Why not? Right, so think about it. Detectability is observability but addressed only to the unstable modes, right? So we're not interested in the stable modes, just the unstable ones. Well, it's the third mode here which is unstable, so we will address detectability, observability, that one, and we need the third column of the CW matrix, non-zero. Well, it is. So by observing the outputs, we've at least got the information that that thing is going to be unstable. So this is a stabilizable and a detectable system, but it's not stable and it's not observable, taken as a whole. So there are the properties of that system. Good. We're almost there, I hope. Right, two forms. I'm not going to labor this one because I've already done it and it's nearly lunchtime. This is the phase variable canonical form, and the only thing that's different between this and the previous slide I showed with phase variable canonical form on it is the title. It's called controllable canonical form. You can arrive at this through the process I showed you in the first section. You get a very recognizable structure of the matrices. You get this one for the system matrix where all the denominator coefficients appear in the bottom row, and the rest of the matrix is 0 except for the superdiagonal, which is 1s. This is because of the choice of states, the state choice being phases. The B matrix, input matrix, is 0 except the last one, and the C matrix, the output matrix, contains the coefficients of the numerator. When you see that, you know you're dealing with a controllable canonical form, and it's called that because this form is automatically controllable. And we're going to use this form this afternoon when we do design for state space systems. Now, there's a parallel form to this called the observable canonical form. I'm going to show you very quickly and tell you that it's related very closely to the controllable canonical form. This matrix, the observable canonical form, something I call OCF, right? So you've got CCF and OCF if you see those abbreviations. The OCF system matrix is related to the CCF system matrix by a transpose. That's all the difference is. And now if you look at the input matrix for the observable canonical form, and you compare it with the output matrix of the controllable canonical form, those two are related by a transpose as well. So, in some sense, the controllable output matrix is the transpose of the observable input matrix and vice versa. And similarly, if you look at the output matrix of the observable canonical form, it's the same as the input matrix of the controllable canonical form, just transposed. So if you've got one description, you've automatically got the other, providing you know how to do a transpose, OCF and CCF. Now, these things are powerful when we come to do state space design later. CCF transformations make the design of state feedback controllers very easy, and OCF forms give the observer designer a hint of simplicity as well. Now, they're called companion forms, and they're related by these transposes, right? It's just what I've explained to you in the previous slide. But this relationship is an extremely powerful one, much more powerful than you might imagine at first. The name for this relationship is called duality, meaning that the two systems described by these matrices are duals of one another. And therefore, you can test for controllability of one by testing for observability of the other, and vice versa, because if you looked at the P and the Q matrices, they were related in exactly the same way. Remember, the P matrix was B, partition B, A times B, A squared times B. Well, when you constructed the observability matrix, it was C transpose in place of B, and A transpose in place of A. Otherwise, they were exactly the same. So when you check for controllability of one, you're really checking your observability of the other one. And this kind of parallelism helps us later when we come to do design, because it turns out that the techniques you use to design state feedback controllers are exactly the same one It's ones that you use for observer design. It's a really powerful thing because you only have to learn one set of processes and you can do both jobs. Now I'm going to conclude this section with a very short tutorial where I'm going to show you what can go wrong. There is a term called minimal realization, which means that you found the state vector with the smallest possible dimension. And what can go wrong is that your model has states in there which are not doing anything. There are too many states. You might have a third-order system, but you've inadvertently given it 4 states. And when you do that sort of thing, things can go wrong. And what usually goes wrong is you lose one of the properties I've just been talking about. You lose, for example, the controllability property, which means that you can't control the system. So you must start by making sure that you've got controllability, and if you haven't, look, are you dealing with minimal realization or not? To illustrate this, I'm going to do it in the form of a tutorial 6.3, which says investigate the controllability and observability properties of this seemingly harmless third-order system with one input, because the B matrix is a column matrix, and one output, because the C matrix is a row matrix. So let's look at this in MATLAB and see what happens. So, nothing very surprising to start with. We will commence by constructing the system. Nothing has appeared in the workspace, but nothing has appeared in the command window, but these are the matrices over here in the workspace. So we've constructed the system. And now we're going to determine, firstly, controllability using exactly the same technique as before. Construct the controllability matrix and determine whether its rank is equal to the size of the system matrix. If it is, then the system is controllable, and if it's not, well, it's uncontrollable, but happily this one is, because the system matrix 3 by 3. This is the P matrix. We're looking for the largest non-zero determinant in that, and it happens that this does actually have a non-zero determinant, so therefore the rank of this matrix is 3. 3 equals 3, and therefore this is a controllable system. Now let's go on and do the same thing for observability. We know already that n is 3. I don't have to recompute it. Observability, this is the observability matrix. Unfortunately, the largest non-zero determinant is a 2 by 2 matrix in here. It has a rank of 2. 2 being smaller than 3, this is an unobservable system. Now, in an attempt to find out why, what I'm going to do next is to look at the transfer function representation of this system. So I'm converting the SS to TF using this script to convert to a transfer function description, and then TF constructs G, the transfer function, from it. So let's look at that. Simply this. Okay, nothing obvious so far. It's a third-order system with 2 zeros in it. And now what we'll do next is we'll use this ZPK script. Remember, this is the one that presents the pole and zero information as arrays. So this will tell us in factored form what the numerator and denominator are, and that'll explicitly reveal the poles and zeros. And at this point, you can see there's a problem, because there is a cancelling pole in here. One pole at s equals -1 and one zero also at s equals -1. This is said to be a non-minimal realization. Now, I'm looking here at a rather simple system. Systems get an awful lot more complicated than this, with many, many orders, and it's kind of hard to find these things. And sometimes you don't want to go to a transfer function representation to look for them. But happily, MATLAB provides us with a script called minreal. See, it's amazing how much MATLAB takes, how much work MATLAB takes out of it. Minreal, you give it the transfer function, in this case G1 is the ZPK form, and it will return another transfer function, which is a minimal realization. In this case, it'll just remove that cancelling pole for us. Now we have a transfer function which is second order, and I can go ahead and reconstruct the state space form of this. Now, the way that I'm doing it, and you'll have to do it this way too, is to get back to these arrays of coefficients from the transfer function description, and that's done with this TF data. It returns the arrays of the numerator and denominator, the coefficients, in 2 arrays, and then you use TF to SS to go back the other way. Transfer function to state space, it takes those 2 arrays and returns the 4 matrices that we need in the state space description. So there we go. There is now a second order system expressed in state space form, which is a minimal realization. And the last cell here simply confirms that we are now dealing with a controllable and observable system. It's the same tests we applied before, constructing the controllability and observability matrices and checking that their ranks are 2 in this case, because the order of the system is reduced by 1. So here we go. The 2 is the order of the system. We've got a 2 by 2 matrix with rank 2. That's the controllability matrix, so we're still good. And now the observability matrix is 2 by 2 and it has rank 2. So now we've got observability as well. So you can run into problems. Those problems tend to be the loss of controllability or observability. And therefore, I'm kind of almost there with this session, and then we're going to stop for lunch more or less on time. Now, the system that I'm going to be using pretty consistently this afternoon for the tutorials is a mechanical system, and it's based on a double mass system like this one, where there are 2 masses, M1 and M2, which are sitting and free to slide on a surface of some kind. So you can imagine these 2 masses as blocks of metal or something that sit on the table, and we can influence their position by pushing from the right on mass M1. And when we do that, obviously M1 is going to move, and its position is called Y1. And as it moves, it will exert a force on M2 because it's coupled to it through this spring damper assembly. Now, these spring and damper values have been chosen such that this coupling is a very lightly damped coupling, meaning that when you give this a little nudge, right, on M1, M2 is going to go boing, yoing, yoing, like this. It's going to go on like that for a long, long time because there's very light damping in there. Now, if I constructed a model of this, just like that, that's probably going to slide along forever because there's nothing to stop it. So what I've done is I've added in a couple of frictional terms in here so that in reality, of course, you know there's going to be friction, and this kind of oscillation is going to die down for 2 reasons. One, because it is a little bit damped, and the other because there's sliding friction here that's going to bring these 2 masses eventually to a graceful halt if we just give it a kick. Now, the variable of interest is Y2. I think what I'm doing here is I am controlling with a force, the force applied to M1, and hoping that Y2 goes where I want it to go, right? And of course, in an uncontrolled, no feedback situation, I'm kind of operating with dead reckoning, really. But you will see later on this afternoon that with the application of control to this, it's amazing how accurate you can get with the positioning of M2, even though there's an indirect coupling between, a lightly damped coupling between them. Now, the reason I've chosen this is that you can visualize what's going on here. There's a nice state space description for it. This is an appendix in the new version of the book, and it's also downloadable from the website as an appendix on that one. So if you go to the website and you look for the 2nd edition of the book, if you don't want to buy the book, you can actually read the appendix here, Appendix E, which actually has all this written up for you. So this is the appendix in PDF form, and you're welcome to download that. Without going into details, these are the equations of motion, and this is how the state equations look. It's 4th order, so you've got a 4 by 4 system matrix, and yeah, a 1, no, okay, it's, what the devil's going on? Oh, yeah. Sorry. There's a little bit more information in there. Can I talk to you afterwards about that? Because I haven't gone through a complete derivation in the appendix. Yeah, it would, yeah. I probably should do that. Yeah, I haven't gone through a complete derivation in the appendix, but the equations here are almost right. The reason that they're not completely right is this. I may as well tell you about it. See, I've just applied Newton's second law to get these 2 terms. There's a frictional term involved in here as well, and because this is the equation concerning the movement of the first mass, there is the input force U that's involved in there. And I've assigned the states to be the position of the first mass and its derivative, so that's the speed of the first mass, and the position of the second mass and its derivative. So when I form the equation for x2 dot, right, that mass times acceleration, x2 dot, equals all this lot. And the problem is that the mass term here appears on the left, and therefore you take all these other terms over to the right and divide through by m1, so that you've got x2 dot on the left-hand side, if you like, which is what I've done here. And the thing that's gone wrong is that I've forgotten to divide this term u by m1. So on this equation over here, this shouldn't be 1. It should be 1 over m1, right? So anyway, I did this 6 months ago, and I went through all the results of this, because there's like 7 or 8 different sections in Appendix E, and all the results were coming out beautifully right. And then I went back to the beginning after I'd published the darn thing and looked at it. I thought, damn me, I've forgotten M1. And you know why I got away with it? Because M1 is 1 kilogram. So for once in my life, I got lucky, right? So M1 was 1 kilogram. Right, now let's just quickly do this tutorial and see how this system behaves. Or doesn't behave, depending on your definition of behavior. Okay, here we go. So we're doing nothing very, and I've corrected it in the script. Here we're creating the model and using the SS function to create the state space model. There it is. And now what I'm going to do is perform a modal decomposition on this, just as I've done before, and we'll see what the modal form looks like. Now, it is, happily, a system with a complete set of eigenvectors, because I've got a fully diagonal modal matrix now. But you can already see that 2 of the eigenvalues are extremely complex indeed, because there's a relatively small real component, but the imaginary component is very imaginary, and therefore you've got a lot of oscillation present in this. And the other thing you can see is that there's a very small number present in the third mode. That it might imply that the system is unstable, but it's not. Actually, that is down to numerical resolution of MATLAB. That is a 0 eigenvalue. We have a modal input matrix, which has got a complete set of terms in it, so therefore the system is controllable, which is nice. You might imagine that from what kind of system it is. And the model output matrix similarly has a complete set of terms in it, so therefore it's also an observable system as well. So far, so good. We can verify this in just the same way as we did before. So let me run down and prove that it's controllable and it is observable. Now what I'm going to do is to conduct an initial condition response of this, and I'm going to extract from the X vector which results, because there are 4 states in there, I'm going to extract the first and the third states from that. Now I've added to it the initial separation between the 2. So these Y0 is a parameter further up, which says initially the 2 masses are separated by a distance, and I think I used about 1 meter or so. It's a pretty big system, this one. And so when I add that to that, and then subtract the first from the third mode, I'm subtracting Y1 from Y2, right, and adding in the initial offset. So this will tell me the separation of the masses over time. And when I run this, you'll see it's a very oscillatory system indeed. Remember, this is seconds now, but you're going to see this come down when we start to control it. And it's very oscillatory, because you're giving it a nudge, and it's going boing, 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 like that. This is the initial condition response. Let me just run back a second and show you what initial condition I've used. This vector here, where I've got the first position mass is a little bit to the right, positive direction to the right, and the second one is a little bit to the left. So I've compressed the spring a little bit, like that, and just let it go. And so this boing, boing thing, it's compressed it 10 centimeters or something like that. It's got all that motion, and that's why. Down here. Now we're going to plot the individual mass positions, and this is the absolute mass positions that are involved, because I'm taking the offset of Y2 into account. Y0 is added to Y2. And you'll see how they behave as we apply this test. There they go. So this is mass M1. It's much heavier, and it's got a bigger frictional coefficient, and it's kind of damped down pretty quickly. And this is mass M2, which is being influenced by M1 to a far greater degree. It's oscillating, and what happens is both of these are kind of oscillating and moving slowly along the slideway, and they come to a rest about half a meter further along the slideway than where they started. So I think you can visualize that by doing that, like that, it's going to oscillate a little bit, and then it's eventually going to move and come to a rest, and that's exactly what it does. We could, if we were so inclined, construct a Bode plot of this, and to do that we need a transfer function representation. So there it is. Now this proves that there's an integrator present. So that very small eigenvalue was 0. And then I've got a complex conjugate pole pair, as you might imagine, and a real pole and a real 0. And all these things can be visualized in the Bode plot, which looks like this. So we've got an integrator, right, minus 90 degrees, and then there is a complex conjugate pole pair, which gives us this and that. And then there's a pole, real pole here, and a real 0 up here somewhere. So these are the properties of the system that we're going to examine in much more detail this afternoon. And the only thing that's left now is my favorite part, I guess, which is the quiz. What do similar matrices have in common? They're similar, right? So they've got something in common. Yeah, they do, actually. Yeah, they do have the same number of eigenvalues and the number of eigenvectors. That's not the answer I was looking for, but it's a great answer. The answer I was looking for is they represent the same transformation in 2 different coordinate frames. But you're absolutely right about that, and that was in the text. 2 advantages of a modal representation, I guess at this point. Yeah, simplification. The pathways from the input and the output to the output are much clearer to visualize. Right? Yeah. So because of the first property that we just said, the properties of controllability, observability, and so on, and detectability and stabilizability, all those things are much easier to visualize than constructing a controllability matrix, for example, and looking for a rank. So it's much easier to visualize those things. How about internal stability for a discrete time system? Yeah, that's steady state. You're right, that's steady state. So internal stability, we call that another name, and Vishal knows it was bounded input, bounded state. So as long as the input's bounded, is the state bounded? If so, it has bounded input, bounded state, or internal stability. But what about this discrete time thing? What about that? What are we saying about the system if it has internal stability? I mean, the internal stability is a bit of a red herring, really. What about the eigenvalues? Stable. The eigenvalues must be what? Right, to be less than 1, or if it's Lyapunov stable, it has to be equal to 1 or less than 1. That's right. When is a system? I've just told you this. When is a discrete time system stable? ISL. Remember what that meant? In the sense of Lyapunov, it's stable when the eigenvalues have a magnitude less than or equal to 1, because actually strictly the Lyapunov stability includes asymptotic stability as well. How can we determine whether a given state space system is observable? There were 2 methods I gave you for this. The first method involved carrying out a modal decomposition. And what did we look for in the modal decomposition? Yeah, that's right. The modal output matrix contained no 0 columns in it. Each of the columns in the modal output matrix, they were gamma 1, gamma 2, gamma 3. Each gamma coupled a mode to all of the outputs. So as long as none of those gammas were 0, you know that all of the modes were coupled through, and therefore the system was observable. There was a test, too. You construct the observability matrix Q. It was C transpose, A transpose, C transpose, and so on. Those partitions, that should have a rank of n, full rank on that observability matrix. So there's 2 different ways of determining that. That's great. How are observability and observable and controllable canonical forms related? There's a word I'm looking for. Duality. They're duals of one another. The system matrix is related through a transpose. So the observable system matrix, OCF matrix, is the transpose of the CCF system matrix. And then you have the controllable B matrix is the transpose of the C matrix and the observable case and vice versa. Yeah, observability is the word I was looking for, and I'll give you that. What is a minimal realization? What characterizes it? Has to do with the dimension of the state vector. It's just a system with the smallest dimension of state vector. That's what it is. The right dimension, in other words. What is the difference between observability and detectability? Yeah. So detectability, yeah, I know what you mean. Detectability is observability addressed to only the unstable modes. It means you can detect instability just by observing what's happening at the output. Now, we're going to break in a moment for lunch, but before we do, I want to thank you for your attention for the last 3 hours, because this is the hard work, right? It kind of seems very abstract. A lot of it is mathematical, and it doesn't look as if we're doing anything real. But this afternoon, please come back, because we're going to use this information to do control of systems like the double mass system and the exciting things like flight controllers. And we use this information in a very real way. All this stuff is important for what comes in this afternoon. So there is, for those of us joining from outside TI, some bags at the back, which we're going to have containing lunch. And we'll come back at 1 o'clock, please, to restart with Chapter 7.